So today we're going to start with a double slit interference problem. This one comes from chapter 17 of the textbook, question number 11. So the question reads, a double slit experiment is performed with light of wavelength 600 nanometers. So real quick, we'll just make note that the wavelength is 600 nanometers. It then says the bright interference fringes are spaced 1.8 millimeters apart on the viewing screen. So I'll just make a note of the spacing and we'll talk about what that means in a second. What will the fringe spacing be if the light is changed to a wavelength of 400 nanometers? Okay, so we know the general statement of the problem, but the spacing may not be immediately obvious. So let's draw a picture to help us understand what's happening here. So we have our double slit and we have our viewing screen. And I'm just going to draw our center line in as a dashed line. And so this is our y equals 0, so this is where our central maximum is located. And our first bright fringe is going to be somewhere up here, y1. And what this means, so we're told that the spacing is 1.8 millimeters. That means that this is at 1.8 millimeters. So our first bright fringe happens at a height of 1.8 millimeters. Our next bright fringe, y2, will be at 1.6 millimeters. Oh, not 1.6, sorry. 3.6. Just doubling it. And so on and so forth. So our next thing we're going to do is we're going to want to write down the equations for a double slit experiment so we can figure out what we're working with. So I'm just going to scroll up. Oops. I'm not very familiar with scrolling in Squid. All right. So we're going to go and look at our interference equations for the double slit. And so we can see that we have theta m is equal to m lambda over d and ym equals m lambda L over d. We have information about ym, so that's probably going to be the equation we want to use. So we're going to write that one down. So we're going to have ym is equal to m lambda L over d. Now, we don't have a ton of information, so this question, that's part of what makes this question a little bit tricky. So we know our wavelength, and we can pick an m value, because we could pick the first bright fringe, the second bright fringe. It doesn't matter which one we pick. I'm going to pick the first one just because it's easy, but you could pick a different one. But then we have this L over D thing, and it's not clear what we're going to do with that. The key thing to that is that L over D is going to be constant. Because if you think about our diagram, and I'll just re-sketch it because I don't know how to find it again. So we have a bright fringe here. This is D, our spacing, and then this is L. So D and L aren't going to change if we change our wavelength because we have to change our apparatus itself. So what we're going to do is we're going to solve to find the ratio of L over D, and then we can use that to figure out how our wavelength will change. So We just scroll over a bit. And we'll rewrite our equations. We have that y m is equal to m lambda L over d. I want to get L over d by itself. So we're going to have that L over d is equal to y sub m over m lambda. And then, like I said, I'm going to pick y1. So we'll say this is going to be m equals 1. So we have y1 divided by 1 times lambda. From here, it's a matter of plugging in our numbers. So we have L over D is equal to, we said it was 600 nanometers, so that would be, that's our lambda is 600 nanometers. That goes in the denominator. Our y1 we said was 1.8 millimeters. So that's 1.8 times 10 to the minus 3 meters. And we're going to divide that by 6.0 times 10 to the minus 7 meters. And then we're just going to scroll over a bit. And this is going to work out to be, if we plug this into our calculator, we'll get that it's 3,000. Note that because our two things were in units of meters, the meters are going to cancel. So our ratio L over D is just equal to 3,000. Now we know what L over D is, we can solve out to figure out what our new y value will be as lambda changes. So we're going to go back to our equation. So we have y, and I'm just going to leave it as y1 because we are still using y1 equals 1 lambda d, 1 lambda L over d, sorry. And so now we want to solve for y1. We know what L over d is and we know what lambda is, so we can say this is the same thing as lambda times L over d. Our new lambda value we said was 400 nanometers, so this would be 4.0 times 10 to the minus 7, not 0.7. And then we're going to, oops, that's the wrong direction. We're going to multiply by 3,000. And we get, this is going to be 0.0012, which will work out to be 1.2 millimeters. So our that new y value, y1, is 1.2 millimeters, and this will also be the spacing. So anytime you're working on a problem and it gives you information about the spacing, that's going to be the same thing as y1, because y1 is your first bright fringe, so whatever height y1 is, that's going to give you the spacing. So that is how to solve question number 11 in the textbook. Up next, we will talk about a single slit experiment, and then we'll talk about thin film interference.